Good morning, everyone. Welcome to the Bloodhound session of STEMfest in Space. Thanks for the introduction, Dallas, and welcome to stage 2. I'm first up. We're going to have a fantastic itinerary today, and you're going to find out some amazing facts. So hopefully the story that I'm going to tell you will lead you into an extraordinary journey of discovery. So if you look at that slide, the first one there, our journey, and it is everyone's journey, but it's the journey in space. And what on earth has that got to do with Bloodhound? So you can see a picture there of Bloodhound, and you can see a picture there of Apollo 11 sat on top of the biggest rocket ever made. We're going to learn about rocket science and where on earth how do we do it? Where are we going to do it? How are we going to apply these technologies? And what on earth has it got to do with Bloodhound? So I'm going to take you on a bit of a journey. So let me start somewhere in the past, because of course, long ago, far away. Well, not that far away. In England, there was a scientist called Isaac Newton. And Isaac Newton, as we all know, invented gravity. Wrong answer. He didn't invent gravity. He found a way of describing gravity in a way that helps us to understand why we don't float off into space. And he was also working on some amazing thought experiments. Now, you and I can do this thought experiment. So what I want you to imagine is a cannon, like a cannon, in the old days, and this is like 1600s. This is a long time ago. Imagine a cannon, and they put a cannonball in it, and they fire the cannon, and the cannonball comes out of the cannon, and he worked out that the cannonball doesn't go in a straight line, that it goes on a curve and then lands on the ground. Up until that point, they actually thought it went in a straight line, but not him. He worked out that it was on a curve. As it lost energy, it fell to the ground. He thought this thought experiment was, if I had a big enough cannon and I put it on a tall enough mountain and I had enough energy, I could fire it into space. And if he could fire that cannon into space, it would keep falling. And if you fire a thing at the right angle with the right amount of energy, that object will keep falling. And because we all know the Earth is round, it would keep falling but never touch the ground. And that cannonball would go into orbit. He published that in 1687, using some maths and science, what we call physics. Now I'm going to show you a picture. This is a picture of a very old book by a chap called Jules Verne, and you can see it's called From the Earth to the Moon. And this is in 1865, and he takes the idea of Isaac Newton over 100 years previous, well, nearly 200 years previous, and he takes that idea of shooting a cannon to the moon so that people, amazingly, could actually leave the Earth and go to the moon and actually land on the moon. What an amazing idea. And of course, that was a book of fiction, not truth, but fiction. Now, I want to move you on, but we're going to move you on very slowly, if you see what I mean. So we're going to take you now to 1892 in Scotland. And in 1892 in Scotland, there was a Scottish scientist called James Dewar. Now, James Dewar was working on some experiments about keeping things very cold, and he found it really hard to do. So he came up with an idea of putting a flask, like you see in chemistry, or that, like those conical flasks, those big sort of circular ones. I've got one I'm going to show you a little bit later. And how to keep that cool, I need to put another one on the outside of it and take all the air from between the big flask and the little flask and make a vacuum. And because I make a vacuum, I can then keep the stuff inside the small flask really cold. Or, of course, you could keep them really hot. And you'll all know and have heard of a thermos flask or a vacuum flask. And that's exactly what John Dewar invented. Now, what on earth has that got to do with rockets and getting to the moon? You'll see. It's really exciting. So people harnessed those bits of science to work out how to get out of the Earth's atmosphere, not using a cannon, but using rockets. And in 1957, October, the Russians put Sputnik, the first satellite, artificial satellite, because in truth, the moon is our actual satellite. And if you get a clear night tonight, you'll be able to see that it's just gone beyond full moon. A week ago, it was full moon. And October is very special in 2020 because it is the only month of the year where you will be able to see 2 full moons. So keep an eye. We can all do that. And we can all see a place where people are going to go in the next few years, not just to explore again, but also to live on. Isn't that going to be amazing? And we all look forward to those times. So 1957, the Russians put this satellite into space called Sputnik. Couldn't do very much, not like the communication satellites that we have today all over the planet. That means I can talk to you even though you and I are not in the same room. And that's because of communication satellites. Another idea started out as science fiction, but became science fact. Absolutely amazing. So we're going to move forward in time to 1961. And in 1961, the Russians, ahead of the game of the Americans, put this man, Yuri Gagarin, into space. And he became the first human being to actually go into space. And of course, they managed to get him back down again, which is really, really important. It's not just about, you know, shooting cannonballs into space, but we need to get him back because he's a person. And it's really important. I'm sure his mum really wanted to see him again. So it's really important that we got him back down to Earth. So you can see here, April 12th, 1961, Yuri Gagarin goes into space. What was happening on the other side of the Atlantic in America was the Americans were, of course, wanting to win the space race. Now, that's a term you can look up online, lots of information about it, the space race. And this was about 2 superpowers, the United States of Soviet Republic, the USSR, and the USA, the United States of America, both in a battle, if you like, to explore space and, of course, then maybe, just maybe, get to the moon. So this is 1961. Now, we move forward in time to the 5th of May, 1961, and I'm going to introduce you to the first American into space. And this man on the right-hand side, that picture in the spacecraft on the left, is a chap called Alan Shepard. And 5th of May, 1961, Alan Shepard in Freedom 1, the little black module at the top, became the first American into space. And in February 1962, a man by the name of John Glenn became the first person to orbit the Earth. So that technology, remember that Newton was talking about getting a cannonball to keep falling but not touch the ground, creating an orbit. Well, they actually managed to do that with the first American, and he became the first person to actually fly in orbit around the Earth. Now, the problem was not getting him up there and getting him into orbit. The problem was, of course, then he is traveling so fast, we then have to get the right angle and the right speed to slow him down to bring him back safely to the Earth. So what did we need? Well, what we needed was amazing maths, and we needed amazing mathematicians to work out the maths you needed in order to get someone in the right trajectory. Try saying that quickly, it's very hard. Trajectory back to Earth. And the person who got those numbers right was a very famous American mathematician who worked for NASA. And that lady, an African-American in this, which is American History Month, was a lady called Katherine Johnson. And Katherine Johnson could see that the maths they needed to get John Glenn back to Earth was not new maths, but it was actually old maths. And the old maths was maths that had been created by a chap called Leonard Euler. And Leonard Euler pinched his ideas and formulated the way he could see how orbits worked by looking at the work of Isaac Newton. And in 1768, this is how old this maths is, Euler published a book with the information that Katherine Johnson needed 200 years later in order to get John Glenn back to Earth. They had a great big computer, a physical machine, but when NASA started work, computers were human beings. They were African-American ladies that worked in the computer department at NACA, N-A-C-A, that later became NASA, that gave the maths information necessary to get people not only into space, but home back down to Earth again. Now, the other cool fact about John Glenn is John Glenn also holds the record for the oldest person in space, because he was a member of the shuttle crew. I'm going to look at the space shuttle. The shuttle crew in 1998 at the grand old age of 77. And I'm not even 77 yet. But it also highlights the fact that, you know, how young someone needs to be to go to space, or how old can someone be to go to space. And there's a lot of conversation going on about long space journeys. And for some people who are quite old, who are actually saying, well, instead of, you know, living the rest of my days in a retirement home, I would quite like to go and do some work on another planet and, you know, end my days there. And there are conversations going on about those things as we speak, because we are looking to explore not only getting to the moon, but also beyond to Mars and who knows where in our solar system. So let's move on. And we're going to move on to a very, very famous event. And this famous event happened in May 1961, when an American president by the name of John F. Kennedy spoke to Congress, which is like their parliament. And he said, I believe this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the Earth. Now, the last bit I think is really, really important. Getting someone to the moon is one thing, getting them safely to Earth is another. Ron Howard made a fantastic film called Apollo 13, which we're not talking about Apollo 13 here, we're talking about Apollo 11, that right at the slide, right at the beginning I talked about, but that proved how important it is to have engineers thinking out of the box, blue sky thinking, or whatever way you want to call it, using what they had to hand, all the things that the people had on the spacecraft in order to solve a problem, which was getting them back down to Earth. So if you haven't seen it, have a look at a film called Apollo 13. And if you want to find more about Katherine Johnson and the others, African Americans that worked in NASA in this month for Black History, then have a look at a fantastic film called Hidden Figures. And Hidden Figures, although fiction, really does tell and capture the story of those people who were absolute pioneers. They were not only women in NASA, there weren't very many women in NASA, but they were African-American women who were pushing the boundaries of what was acceptable in that day. And in the 1960s, of course, when we look back, some people, because of their color, couldn't even sit in the same part of a bus or even go to the same school. Time moves on, and we need to make sure that we use all the people that have the skills, regardless of their color, regardless of their background, regardless of their age, to be able to solve the problems of right here and the future. So in setting that goal in 1961, he made something extraordinary happen. And we're going to talk about that in a moment. But what I want to do first is what I want to do is actually show you how on earth did we get out of our world into orbit and to Mars. And I'm going to talk about rocket science. So rocket science, what on earth is rocket science? Now, maybe, you know, your mum or your dad would have said, oh, come on, it's not rocket science. Well, whoop, whoop, whoop. This is rocket science. I'm going to show you a little video that my friend Stefan Marjoram put together, and a desktop experiment like no desktop experiment you've ever seen of what is rocket science and what are the types of rockets. Then I'm going to show you. Have a look at this video. It's really, really cool.
All rocket types need two basic ingredients, fuel and oxidizer, so that the fuel can burn. Solid fuel rockets are the most common. Here, a powdered mixture of solid fuel and oxidizer is packed into a casing. Once it's ignited, the mixture rapidly combusts, propelling the rocket forward. It's very simple and safe until it's lit. but has one drawback. It's not easy to turn off. In a liquid rocket, liquid oxidizer and fuel are kept in separate tanks. These are then pumped into a combustion chamber where they react violently with each other, sending hot gases out of the specially shaped nozzle. The rate at which the liquids are pumped can be varied to alter the amount of thrust, and it can even be shut off altogether. But if these liquids accidentally made contact outside of the combustion chamber, they could cause an explosion. The third type of rocket uses elements of both other systems. The oxidizer is stored separately, and the fuel forms a solid lining on the inside of the rocket tube. In Bloodhound, the oxidizer is high-test peroxide, or HTP. It is pumped through a silver-plated catalyst, which causes it to decompose, releasing very hot steam and oxygen. This is hot enough to ignite the fuel itself and create thrust. It's a fairly safe system, as stopping the flow of oxidizer will stop the rocket, and the fuel is a harmless rubber mixture. Our resident rocket expert has built a small hybrid rocket which we can run in the workshop. It uses a Perspex tube as the fuel, so that we can see what goes on inside.
As you can see, this is just a stick of plastic, and I guess the worst thing that could happen is you could drop it on your toe. So we'll ignite the hybrid on a count of 5, 4, 3, 2, 1, go. Although the motor we'll be using on Bloodhound will be quite different in terms of size and oxidizer, in fact it'll be hydrogen peroxide instead of oxygen that we've used today. It will also use a slightly different fuel that's based on a rubber instead of acrylic, and obviously it'll generate a great deal more thrust, but the principles are exactly the same. And in fact the safety of it should also be almost identical, which again is very, very important for our vehicle where we have Andy Green driving it, and you'll want to be able to shut off that rocket motor at any point that he deems necessary.
Brilliant. Thank you ever so much, Stefan. Now I'm going to show you these three types of propulsion. Now you can see this here, you may be familiar with this. This is a Bloodhound rocket car. It's one of the workshops that we do. By all means, click on the link on my profile and you can see these workshops. And this is just one of the high-speed workshops that we run at our education centre, or when we can get out to schools. Now, what you may or may not know, so that uses a solid rocket. We set fire to them by using electrodes. So it's just an electric circuit, burns a tiny little bit of material and sets fire to the black powder. Oxidizer, fuel, whoosh. They're on a tether line so they don't go off all over the place, because that's quite dangerous. And these can go very, very whizzy. In actual fact, the model rocket car world record currently stands at 533 miles an hour. And that was set by Joseph Whittaker School in 2014. Amazing. So solid rockets can be incredibly powerful, but you can't really switch them off. So once they're going, they just keep going. And there's not much you can do about it until they burn out, but very, very powerful. So we don't want to use that with a human being in it, because in actual fact, the amount of energy, even in one of the little motors we use, that would be enough to make Andy 7 times heavier, 7G, increase his gravity. Remember Isaac Newton? And we are at 1 gravity, wherever we are, we're at 1 gravity. As you accelerate, you increase your gravity. So you appear heavier. You don't increase your weight. You change your mass, you change your weight. So you look the same, you are the same, but you feel heavier because it's being pushed down. So Andy would be weighing 7 times more. Now that's quite a lot of energy to put up with. Now here's a picture, an iconic image of actually the launch of the Apollo 11 spacecraft in 1969. And in 1969, that Saturn V rocket that is underneath Michael Collins' Buzz Aldrin and Neil Armstrong in the little module at the top, the command module, is the most powerful rocket ever designed and built. Others have been designed, but they haven't been built and working successfully. So let me just give you some numbers about how powerful this liquid rocket, using, remember, the technology of the Thermos Flask, and we're going to do a bit of a recap after this, means that they can create an awful lot of heat and energy. That is the biggest rocket ever. It's 111 meters tall. It weighs as much as 400 elephants, not 4, not 40, 400 elephants, and it creates 160 million horsepower. That is a lot of horses. But it's very powerful. And that goes back to a measurement of steam engines that was created, a means of measure, by a man called James Watt, who created steam engines. Well, in actual fact, he pinched the idea from somebody else. But what we talk about his steam engines. Top speed, 6,164 miles an hour. Very, very fast. We're not going to use that in Bloodhound. Look how enormous it is. It's way, way too big. We have a limited amount of space in Bloodhound, the car. Even though it's just under 14 meters long, it's certainly not 111 meters long. So that's just not going to work. What do we use? Well, we use what's called the hybrid rocket. That was the third type of rocket and the desktop experiment that you saw. Here's a picture of it, and I'm going to show you a video of when we tested this hybrid rocket from the NAMO. You can see the name there on that slide, who design and develop rockets for the European space program. So space is very much to do with the technology here, which we also use in Bloodhound. So we're learning about rockets. I haven't got on to where the connection with Apollo 11 is. Just wait and see. Let's have a look at this video. It's amazing how much power, energy, and heat is generated from this very special hybrid rocket. Look how small it is in comparison to Saturn, but also see how powerful it is.
So with our partners NAMO, we're about to witness the test firing of their hybrid rocket motor in their test facility in Norway. For us at Bloodhound, it's immensely exciting because this is the motor that's going to take us to break the record, developed with ESA, the European Space Agency, a hybrid rocket motor that's going to power the future generation of spacecraft. And that's what's going to be powering the car from next year. So for us, it's a really important test.
This is the NAMO hybrid rocket. It's a hybrid rocket because it's using a liquid oxidizer, in this case hydrogen peroxide, and a solid fuel. The oxidizer passes through this pipe here. It's then going to pass into the catalyst pack here. The catalyst pack degrades it into both steam and oxygen at very high temperatures and pressure. The pressure coming through here is apparently enough to fill a bath in 3 seconds or so. It's then going to pass into the combustion chamber where it mixes with our fuel. It's then combusts. This will get extremely hot and then pass out through the nozzle off this way. Hybrid rockets are relatively new technology compared to other types of rocketry, and it's the safety element that really appeals to us. This is going to provide half of the thrust that leads us to 1,000 miles an hour effectively, so it firing is a very big milestone for us.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1. That's perfect.
From our perspective, it was really good because there were no real surprises. So the rocket burned very efficiently. You can see that from the really clean rocket efflux. It's a huge step forward and massive confidence boost for us running in the car next year.
So there we are. What an amazing experiment. And that's what it is. It's research and development. And research and development is critical to make sure that we get everything working not only efficiently, but more critically, safely. And remember what was said in the video there, how safe this this type of rocket is, because we can literally cut off the supply of oxidizer. We need 3 things to make fire, remember: fuel, oxygen, and heat. So if you stop the oxygen, you put the fire out. That's how fire extinguishers work. You take away one of those sources. So either heat with a water extinguisher, for example, or oxygen with a CO2 extinguisher. So 3 things to make fire, and that's how rockets work. Same principle, makes no difference. So now I'm going to show you some experiments to see these 3 types of rockets in action. So here we go. Okay, so now you can see I'm in my son's bedroom. That's, you know, we're living in a world where broadcasts are being done from kitchens, dog houses, you know, and bedrooms. So yeah, here I am. I'm going to just go through a little bit of a recap and also show you some of those things that we talked about in terms of rocket science. So rocket science. So here's the first. So the first one of 3. So the first one of 3 is this, which is a solid rocket motor. Now, the difference between solid rocket motors is actually determined by the information on the top. And the information on the top actually tells me, in effect, how much powder is in there. So depending on how much powder will determine how long it burns for, and therefore how quickly the thing can go, yeah, essentially. So the record cars weren't using rockets like this. No, they were using rocket clusters, and they had an explosive license, and this was a school with an explosive license, you know, like most schools. No, like hardly any schools. And they were making their own rockets, making their own launch equipment, electronics, and all kinds of amazing things in order to break that record. You know, STEM clubs, the world is your oyster, and limitless in terms of what the possibilities are. So as you see up one end, this is where I put the igniter. This is actually clay, and it holds the igniter into position. And then once I press a button on creating an electric circuit, putting an electric charge through, burns a little bit of material, and then burns the black powder, and you can see the residue on the side there, which then moves it forward. It's really simple. It's exactly the same principle as making a car like this and sticking a balloon on it. Because as you know, every action, i.e. me blowing air into that balloon, produces a reaction. So the car is over here, you can't see the car. I blow up the balloon, I let go of the nozzle, and whoosh, and it goes from there to there. So action, reaction, and that will keep going until it meets resistance. And of course, on the Earth, air causes that resistance. So you can make one of these, and you can go to our website to find out how. But that's just simply using a gas called air, which is made up of lots of different gases. As you know, 70% of it is actually nitrogen, what we're breathing in all the time. There's oxygen, carbon dioxide, and other gases. But essentially, you blow air in, you get air out. You knew that when you were 3. Every action, so I'm just going to do that. Every action has an equal and opposite reaction. Should we do that again? Every action, you have to say it and do the actions at the same time. Every action has an equal and opposite reaction. That's how it works. Isaac Newton, by the way, came up with that. 1600. Remember him with the cannonball going whoosh and then falling, but keep falling, so it goes into orbit. So we've got that. We then move on to, remember, John Dewar's invention, the Thermos Flask or the vacuum flask. Now here is some liquid. In actual fact, I'm quite thirsty. So this has been here for some time, and as you know, because it controls the heat, the impact is if it's hot, it should stay hot, and if it's cold, it should stay cold. So you can get them for like soup and stuff, but you could also put, for example, ice cream in it, and it would stay ice cream. Maybe you could try that if you've got one. I don't know what ice cream you like. I don't think the flavour has any impact as to how cold it gets. So if I open the lid on my Thermos flask, what you see come out here, can you see it steaming up my glasses, is steam. And if you remember, and it does look a bit like a rocket, that Saturn rocket, instead of having liquid H2O, water, so H2O, if you wrote that down, maybe write it down, H2O, and H2O has two elements. So we have a thing called the periodic table made up of all the elements on the planet and in the gases around our planet, and two of them are hydrogen and oxygen, and these work fantastically well when you mix them together and set fire to them in a controlled way, otherwise you get boom. So the steam, imagine steam coming off, it's literally, you open the lid, and the most effective way of doing that in the 1960s was the Saturn V rocket. And that Saturn V rocket was a NASA engineer, I've got his name written down here, and his name was called Werner von Braun. And Werner von Braun in 1960 came up with that way of using this really old technology from Scotland in the 1800s and using it in the Saturn V rocket. Way more efficient, effective and powerful than, as I say, currently any rocket ever built on planet Earth. They are building larger ones now, they're working on new technology, but right now that's the biggest. So Thermos Flask, John Dewar, we can go to the moon. So let's do a little bit of a recap where we are so far. So we go back to Newton. Newton's thought experiment, close your eyes, think of a cannonball on a mountain, really big cannon, lots of energy, cannonball, throws it on an arc, and instead of hitting the ground, because he's thrown it so far up and out, it keeps falling, but never touches the ground because the Earth is round, creates orbit. And then of course, from there, we move on, and that means that we then get to Mr. Jules and Leonard Jules, using maths, ideas from Newton, curves, is the equations that Katherine Johnson uses in 1962, not only to get John Glenn into orbit, but to get him home again. Really, really important. So Katherine Johnson, 62, uses Euler's equations, really old equations, inspired by Newton, to get John Glenn back home again. Really, really important. So we now move on, and there are some people I'm going to talk about in a little while that got inspired by Newton and Euler in order to come up with their own equations to get the right shape. And they did that in the 1800s. We're going to talk about them in a bit. But we move on to hybrid rockets. Hybrid rockets, remember, you may have seen them now, hybrid cars using probably petrol and electric. So two types of fuel, two types of energy in cars. And as you know, UK government have already decided by the time, all of us in the next few years are all going to have to drive cars powered by something other than petrol and diesel. Now, I used to say in the future we're all going to have to drive electric cars, but they're working on other technologies. They're working on things called hydrogen cars, because that would actually be more efficient, and we can harness those forms of energy from things like water and air, because the air around us has H2O in it. Now, what do I have in here, in this conical flask? So in this conical flask, I have H2O 2. So add a 2 on the end of your H2O. So you've still got the hydrogen and the oxygen, but you've got your H2O2. So it's not water, it's something else. It's called hydrogen peroxide. Hydrogen, H2O, and an extra oxygen molecule as part of it. Really, really important. So I've got the hydrogen, oxygen. Now, what I need to do is split the hydrogen and oxygen apart. And then what I'm going to have, because I've mixed in there some washing up liquid. And because I've mixed washing up liquid, the gas bubbles that are going to be generated when I create the catalyst. So I've got a catalyst I'm going to use. It's something called potassium iodide. And this potassium iodide, when I mix it with this hydrogen peroxide, will do something amazing. What it will do is cause a chemical reaction, and it will speed it up really fast. Now, what we should see is 2 things, the same 2 things that we will see from the rocket from Bloodhound, which is oxygen, but because I've got washing up liquid, you can see the oxygen bubbles. So it'll create a lot of bubbles. I mean, I'm loads of bubbles. That's why it's in this blue tray. Otherwise, it'd be all over the bedroom. That's a bad thing. And then steam. So hopefully you'll see some steam coming off the top of the flask too. I hope this works. That's why I've got some gloves on, because H2O2, you may have heard of it. It's hydrogen peroxide. Peroxide? Who's ever been to a hairdresser? Now looking at some of you, you need to go. Hydrogen peroxide is what hairdressers use to bleach hair. Peroxide blonde is bleached hair blonde, but it's not as concentrated as we use in Bloodhound. That is 87.5% proof. If that came in contact with you, you would be a memory. The stuff I have here is 35%. You have to be kind of like certified special to get hold of this. The stuff that hairdressers use is about 6%, so just enough to strip the colour out of your hair, but not to make all your hair fall out, because they wouldn't be hairdressers for very long if they did that to everyone that walked through the door, would they? Anyway, so here we go. Let's hope it works. Chemical experiment, safety first. So it's in a container. I've got gloves on, and I'm also going to put these goggles on just in case there's any splash. I don't want to get it in my eyes. That would be a bad thing. So what are we going to do? So here we go. Potassium iodide, a spoony thing. And I'm going to take the spoony thing and I'm going to put in the potassium iodide into the flask. So this reaction should happen very quickly, if it happens at all. As you can see there, it's bubbling up and it's all coming into the good, isn't it? Can you see all the steam coming off? And the bubbles smell beautiful because of the washing up liquid. It's lemon flavored washing up liquid. So it's producing a lot of heat. And in actual fact, did you notice in that video the heat that was coming off the nozzle at the back of the rocket in that NAMO experiment would actually get to 3,000 degrees. 3,000 degrees is twice as hot as a volcano, and not as hot as the surface of the sun, as you know, which is 5,000 degrees. 5,000 degrees, but 3,000 degrees, a lot of heat, which produces thrust. So the gases expanding, forcing out the back. In Bloodhound, do this, whoosh. In a rocket, do this. And incidentally, if we put Bloodhound on its end, it would go to 25,000 feet because of the amount of energy created from our rockets. So there we are. I hope you really get to understand how cool this technology is. And it's not science fiction. This is science fact. Now, we need to go back to our story. How is Bloodhound connected to Apollo 11? And now back to Apollo 11. Now, Apollo 11, you can see here in this picture that no one took that photograph because there was no one in space, like taking pictures of the command module and the landing module there, Eagle. This is Lego, so you can buy one of these. In actual fact, one of our team members, Mike Ford, has got the collection with the Saturn V and this are really cool models that you can get now from Lego. So Apollo 11, 1969, this iconic photograph of Neil Armstrong's footprint becomes the first human being to land on our nearest satellite, because satellite is a word of that describes those things in space, not just artificial ones like Sputnik was. So here we are, Neil Armstrong actually walking on the moon, 20th of July 1969, fulfilling the brief that John F. Kennedy had laid out earlier in the decade. So there we are. So we're going to move on, and here we are. Here's the connection with Apollo 11. This photograph taken way back in 2010, November of that year. Neil Armstrong himself came along to the Bloodhound Technical Centre to see Andy Green and the rest of the Bloodhound team. What an amazing time. And the reason why he came was not only did the effect of the Apollo program, what's called the Apollo effect, inspire a whole generation to take up science, technology and engineering jobs in the 1970s because of the space program, very exciting and really attracted people to get into science and technology and engineering. But of course, we need to continue with that and create another Apollo effect. And Neil Armstrong quite amazingly said that he saw that Bloodhound was doing that and came along to the technical centre to show us. So what an amazing time. And we've met other members of the Apollo program who have come along to Bloodhound events as well, because we're trying to create similar kinds of technologies. And you've seen the propulsion, European Space Program. We move on. So within the space program in the 1970s, so 69, Neil Armstrong goes to the moon, 1973, 74, Skylab. Now Skylab was a place where they could do experiments in space. It kind of looks like they've got a bit of brown paper on the outside. Didn't last very long, but pioneering work in space to start some new things. Now I'm going to show you a photograph of the first British astronaut in space. No, not him, her. Yes, there we are. So, so this young lady, Helen Sharman, slightly older now, in 1991 went to the Mir space station, a Russian space station, and she is a chemist. So she was doing chemistry experiments on the Mir space station, became the first British astronaut in 1991. Amazing, groundbreaking work that she did and paving the way for others. To get into space, remember John Glenn? John Glenn, when he was 77, went in one of these, the space shuttle to take things up to space, do experiments, launch satellites, and of course it would fly back to Earth again. And they ran from 1981 to 2011. Amazing stuff. And one of the things that they helped to create, which is really important, and you can see them in the sky at night even now, and if you've got a really good telescope you can actually make out the shape of it, is this, which is the International Space Station, made up of lots of different components, much bigger than Skylab was, and of course is still flying around thousands of miles an hour, going around the Earth as we speak, doing experiments. And if you remember, somebody called Tim Peake, the second British astronaut, went to the International Space Station in December 2015. I'm going to show you two photos of him. Yeah, there we go. There he is in his space outfit. And look there he is at New Scientist Live, where he came along to the Bloodhound stand because, of course, he's really engaged with the kind of science and technology that we're working on, because it's really important stuff, and doing the same kind of thing that he tries to do. And of course, this STEM Fest in Space is trying to do about inspiring you to get curious about space and maybe even look at the kind of jobs and technology and engineering that we are all going to need in our futures. So let's move to right here, right now. And on the 2nd of May in 2020, that's this year, the Dragon 2 rocket, Elon Musk, SpaceX, was launched with a manned crew to the International Space Station. Amazing technology. And one of the bits of technology they used, this is a different photograph. This is a pressure photograph. So you can see here, they have to make it the right shape and they have to make it out of the right materials in order for it to work properly. And this technology is called computational fluid dynamics. Now, computational fluid dynamics is trying to solve equations, and computers now solve those, or try and solve those equations to do with pressure, air being a fluid, computational doing calculations, and dynamics is movement. And you can see here a picture of that module coming back to Earth. So they've got to get it right. And equally, it's been used on Bloodhound. Computational fluid dynamics, where did that technology come from? Well, a couple of scientists in the 1700s, mathematicians inspired by Euler, of course, and Newton, come up with the equations that help to shape not just Bloodhound, but spacecraft in the future. Amazing technology. The other part of the technology where we have connections and links with space is 3D printing. And here is one of the examples of the 3D printers that is actually on the International Space Station. And they have actually printed and continue to print 3D printed items on the International Space Station. Not just physical things like solid objects, like made of plastics and things like that, that you may have come across, but also made of other materials like chocolate. Well, no, they're not doing that in space, but you can get a 3D printer to print chocolate. Isn't that really cool? And also metal, and components on Bloodhound have been 3D printed out of carbon and metal, showcasing exactly the same technology. And here's an example of one of them. The steering wheel on the car is 3D printed. Why? Because it fits Andy perfectly. Clay mold on his hands, he leaves an impression, they scan it, and then using that information, height, width, and depth, they can then print it using titanium dust, and a heat source grows a steering wheel out of titanium metal. And I'm going to show you some examples so that you can see this for yourself. So as you can see from that slide, the amazing technology that is used in Bloodhound, and we've also talked about how this technology is being used on the International Space Station for space 3D printing. So I wanted to show you some examples of 3D printing. First of all, I'm going to take you back to my little car, and you think, why have you taken me back to your little car with the balloon on the top? Well, the little balloon on top of this car, in actual fact, is 3D printed. What do I mean by that? Well, it started out as a single sheet. In actual fact, I have an example here that I can show you. It's just a sheet of foam, but a sheet of foam, if you know what a sheet of foam is, it's very floppy. I could make it into a hat or anyway, it's very floppy. You get the point. So I have to make that structure stronger. And the way I make that structure stronger is by laminating it, putting layers together. And additive manufacturing is doing that. So it's adding layers. And you can see here that in actual fact, even the wheels have been used from that sheet of foam, and the body of the car has also been used by layering up the pieces together. There we are. Anyway, so you can see. So in very crude basic terms, that is a 3D printed car. Started out as a single sheet, ended up as a three-dimensional object that actually moves using thrust by putting gas. Remember we talked about blowing up the balloon, whoosh, action equal opposite reaction. So examples on Bloodhound. Carbon air intake, actually made out of carbon, black carbon dust, grew into a nozzle that was helping to cool the body of the car at the back of the car, and this was 3D printed. Other components within the car, and I showed you the steering wheel. Now this is not far away, it's very small, it's not actual size, but it's made on the same machines by Renishaw, one of Europe's leading additive manufacture companies based in Gloucester in England. And you can see here, this is using the same software, and it's made a little model of Andy's steering wheel out of the same material, which is titanium metal. So taken titanium dust, heat source, and then grown a steering wheel out of it. You can see here at the back, we'd fill in it with some triggers. In actual fact, the triggers, so efficient, so effective, it's from a Black & Decker drill, just so you know, bit of knowledge there. And there it is, a steering wheel for a very tiny Andy Green, but there it is. One of the other components on the car, critical component on the car, is this. Now, I wonder if you can work out what that is. It's the pointy end. So the pointy end, so obviously that's at the front, and that section is the nose cone. And that nose cone then goes on to carbon fiber, which is very light and very strong, but would be brittle if impacted by friction of air and dust coming off the desert's floor where we ran the car. That picture at the beginning you saw. Hatskiin Pan, South Africa. So titanium, very hard, very strong, and can withstand friction from air, because the friction from air from Bloodhound would get to a mere 120 degrees. Remember that Dragon capsule coming back to Earth, thousands of degrees being generated as it returns to Earth. So 3D printed out of titanium. That's components on the car. Now this component here is made out of a different metal. Remember that periodic table? And this is a metal called aluminium. Aluminium. Now aluminium, you take a mineral called bauxite, because it's one of the third most prolific minerals on the Earth, and that then allows you to create aluminium ore. So you take the ore and you create aluminium, and this particular piece of aluminium, 3D printed, is a hinge from a prototype electric vehicle. Why am I showing you that? Well, because this is right now, but what we're also talking about is the future. So here's some examples of 3D printing now, but the last slide I'm going to show you is an artist impression of the future. So our journey so far has taken us all the way back from Isaac Newton, and we're up to the present day. So let's now have a look in conclusion at where we're going. So here we are. This is another part of our journey, a part of the journey that hasn't even been written yet. Starting with Isaac Newton back in the 1600s, imagining in his mind shooting cannonballs into space to create orbits. Katherine Johnson using maths that Euler, inspired by Newton, created in order to get John Glenn back to Earth, orbits being possible with people, human beings outside of our planet Earth, to get and enable people to go to the moon. And in 1969, Neil Armstrong and Buzz Aldrin became the first human beings to actually land on the moon. But this picture here is not a photograph of Neil Armstrong. This is an artist impression of the future, which draws all of those technologies together that we've been talking about in this small part of our space journey to do with Bloodhound. We talked about rocket science and the kind of rocket technology not only being developed now, but there is rocket technology developing for the future for further space exploration that we haven't even had time to talk about, using some very old maths and science and incorporating new technologies. This is a 3D printed space station on the moon because NASA are planning now the next part of their adventure into space. You may have seen it, it's called Artemis. So we've heard of the Apollo program, and now we're talking about the Artemis program. And Artemis 3 in 2024 will look to put human beings back on the Earth over 50 years from the last time that we went to the moon. Now, who are Apollo and who are Artemis? Well, Apollo and Artemis, they've taken those names from ancient Greek mythology. Wow, that means we've actually taken our journey 3,000 years back into the past. Apollo and Artemis were twins. Apollo, the god of the sun, and Artemis, the god of the moon, twin sisters. And together, they worked together, and their famous invention in Greek mythology was the bow and arrow, the crossbow and arrow, which, of course, fires an arrow, and as Newton demonstrated with his cannonball, what it do it would do exactly the same thing, flight. So isn't that amazing, the journey that we've taken on? But this is a journey that we are all a part of. You see in that photograph, planet Earth. Well, imagine planet Earth is just an object like a spaceship, traveling through time and through space. We are all on this spaceship called planet Earth. We need to look after that environment that we're a part of in order for us to create technologies to look after our spaceship as we fly through our universe and allow others to explore places like the moon, Mars, and beyond. By 2030, through the Artemis program, we would hope to see human beings on Mars. What an amazing journey of science, technology, and engineering, and of course, maths. Without it, we couldn't do the things that we're going to do right now and in the future. And if we work together to solve problems, then we can achieve anything. I hope you've enjoyed our little journey at the start of this amazing adventure, which STEMfest in Space is all about. So much to explore, so much to get involved with. If you want to know more about what we are about, Bloodhound, and the kind of activities and workshops that we provide and resources on our website, then simply go to the profile on the STEMfest website. Also, as well, there's a little video, which I really love, of another person who's creating a journey and a story called Richard Branson. You may have heard of him, writing a letter to his grandson, talking about what I've just shared of this amazing journey. Space is not a destination. It's a journey that we are all a part of. Thank you ever so much for listening. Have a wonderful day. Make the most of this opportunity through this day and link up with as many of the broadcasts that you can. Thanks for watching. Thanks for listening. Bye for now.